Thank you for sharing your lunchtime with me. Today we'll be talking about, industrial decarbonization solutions and if or how policy interventions can improve the economic viability. I'm just taking one for the team, but this is work that was done by three people, Harry, Gila, and Ed, looking at all the case studies. Before I go on, I would like to ask a question. I want to know what you think. So, do you think the industrial sector needs financial support, or should they be mandated to do the right thing? What do you think? Do they need some financial support, or should it be passed into law that they need to do the right thing? Full stop. Both? Okay, thank you. Yeah, yeah. Anyone thinks it should just be mandated to do the right thing? Mandated to the right thing? Okay, okay.
I think it's difficult to mandate something globally.
Yes, yeah.
So I think it's kind of carrot and stick.
Yeah, yeah.
And also they're complex value chains. So how do you ensure that burden's
shared? Yeah, yes, yeah. Yeah. So I'm happy to hear that, majority was not to mandate something because bulk of my research is on the financial interventions to support industry. And I know that it's not just financial interventions. We need legislation and we need mandates. But my expertise is on these financial interventions. So what I look at in my group is I develop models to evaluate how these market interventions or financial interventions can improve the economic viability of industrial decarbonization solutions from the bottom up, so from the firm level. So I look at CCUS, fuel switching to blue hydrogen, green hydrogen, electrification of industry, direct air capture, and production of e-fuels for aviation and shipping. And I majorly look at how to improve the economic viability in 6 sectors: iron and steel, cement, chemicals, refineries, petrochemicals, shipping, and aviation. I mean, the justification for these sectors is because they are responsible for 31% of global carbon emissions. But also, my primary background is process engineering, and I used to work as a process design engineer for the energy intensive sector. So I have an idea of what happens on the plant level or on the firm level. Now, in my group, we estimate the economic viability on a mesoeconomic scale, so from the bottom up. So what can work for plants all over the world, and then look at what is happening today and see how we can move them further along to get to net zero or to decarbonize. Now, the whole, if I could represent my research in an image, is now there's a price gap between sustainable solutions and business as usual, unfortunately. So, clean solutions or sustainable solutions come with an added cost. Now, interventions are supposed to bridge this gap over time, right? So you could have interventions from the technology side, like improving the performance of a technology, finding the optimal operating conditions. And what we've seen from the work we've done and the case studies and the data is they are not sufficient to make them competitive with the business as usual. And then you look to policy interventions just to create a business case. Again, from what we showed today and what we've seen, it still doesn't get us to be more competitive with the business as usual, to establish a business case for decarbonization. And we look to private finance mechanisms like sustainability-linked bonds. It still wouldn't get us there. So we need to also intervene on the business as usual side by using the incentives like taxes to bring up the price and to reflect how their carbon intense nature. And what we've seen is over time, we get to some form of an economic tipping point. So what we do is to build models to show how any intervention can get us to that economic tipping point and when, from a plant level and from a technology perspective, and how the cost can fall over time because of the demand pool created from those interventions. So our core expertise is building these models that we apply to different things. So we look at the impact of internal intervention, so what you do with process integration, what you do with energy efficiency. We also look at the impact of external interventions, which could come from policy, so capital grants, feed-in tariffs, carbon contract for difference, tax relief, carbon abatement incentives. And we look at market shaping mechanisms as well. So where you have advanced market commitments, some form of concessional capital, offtake agreements. And the whole point is, so these are the list of market-based policy support around the world. The whole point of what we're trying to drive out is how you can converge what you could do with the technologies, what you could do with public finance, policy interventions, and what you could do with private finance to bring those tipping points forward, so we can create a business case for industrial decarbonization that aligns with whatever mandates and legislations is available in different parts of the world. Because the thing about industry is they can't create the demand pool the rest of society needs. So if we make it cost effective for industry, then decarbonization will be cost effective for the rest of society. So that's just an introduction to my research group. But today, I'm going to talk about how policy interventions can move the needle for industrial decarbonization. And I'll start with a background, and I'll consider just a slide each for the sectors I'm considering, and I'll go into the methodology and present the case studies, and then get to some conclusions or some thoughts for future work as well. Now, industry is interesting. So I'm looking at manufacturing. It facilitates the transition to net zero because you need to manufacture low carbon solutions for transport, for power, for buildings. But the industry also complicates the transition to net zero because it's a global market. There's a lot of heterogeneity in this space. Plants are different, owned by different people. So it complicates that transition as well, and it's expensive to decarbonize, and that's why they're called hard to abate sectors. But industry also makes significant contributions to the economy. And within the industrial sector, there are 5 heavy sectors that are responsible for 80% of industrial emissions. So today we're looking at cement, we're looking at steel, and we'll look at ethylene. So ethylene production is that part of chemicals that is responsible for majority of the carbon emission from the chemical industry, and look at if today's policy interventions are sufficient to make decarbonization solutions for these 3 sectors cost competitive. We look at iron and steel from the global scale to ethylene within the EU and cement in 4 countries. Now, there are several barriers to decarbonization of industry. There is the lack of skilled workforce. There is industrial characteristics. They're very conservative because they have very long technology lifetimes. There's a bit of lobbying going on. There are technical challenges, so infrastructure, for instance, supply chain challenges. And you still have some regulatory challenges, unclear policies, you still have increased risks. But my research addresses these financial challenges. So how do you make the process and the technologies and the plans more economically viable? How do you overcome this barrier of high investment cost and long payback? But I recognize that there are other challenges to address, so I can only pick 1 or 2. Now, if we start from the iron and steel sector, I mean, we have about 6 million individuals working for the iron and steel sector around the world. And we have the revenue from iron and steel trading is about $2.5 trillion. So it's a big deal, this sector. And so far, we've demonstrated technologies that can decarbonize iron and steel manufacturing, from carbon capture and storage to capturing CO2 from the process, to using hydrogen as a redundant. It could be blue or green hydrogen, to electric arc furnace. And all these technologies have been demonstrated at scale. The challenge is, in my opinion, because of my expertise, is how you make them economically viable. Now, the same for ethylene. So ethylene is one fundamental primary material present in plastics and a lot of other compounds that we use daily. Your chair, my jacket, is not 100% wool, so there's some polyethylene there. Your laptop, lanyards, everything has ethylene in them. And within the chemical sector is the second largest emitter of CO2. Now, there's a new production process for ethylene that relies on green hydrogen and CO2 to make methanol. So it's methanol synthesis and methanol to olefins. I'm still cracking my head around the process, but I've got the economics right. So if you ask me any questions on the MSMTO process, I won't be able to answer. But on the economic side, I will be able to answer. So there's that process that happens to be the most cost effective when you compare it to other ways of decarbonizing ethylene, but it still doesn't make clean ethylene cost competitive with the business as usual ethylene. So that's one from the chemical industry. And finally, cement. I mean, cement is really all around us. If we estimate the cement per living person, everyone requires like 530 kilograms of cement. And that's responsible for around 6.5 of all anthropological emissions, or all man-made emissions. Now, decarbonizing all cement plants, there are over 3,000 cement plants in the world, will cost about 1,500 billion US dollars, so like $1.5 trillion. So that kind of negates the revenue from iron and steel, for instance. So these are huge financial investments to decarbonize the cement sector. And on the pathway, you see the most promising is carbon capture and storage. So one of the case studies will look at CCUS for decarbonizing cement plants. Now, there are key questions that we answer in the space of policy interventions. Number one is, how effective are they in reducing cost and generating demand for the technologies? Are they sufficient? So can they work? Can they change the balance, the economic balance when it comes to industrial decarbonization solutions? Then we ask ourselves, what's the best mix of policy interventions? Do you just want carrots, or do you just want to incentivize like in the United States where we have so many carrots, or do you also want to penalize? So taxes, so sticks, what's the blend? Is it best to have carrots and sticks? And what's the optimal mix of interventions for a win-win situation? So this is looking into the future. And we answer these questions by modeling on a plant level. So the mesoeconomic scale to see the impact of these policy interventions in the plan, because plans need to make decisions to invest so we can have projects that become live with time. So the methodology is quite not so simple, but simple, right? So we just develop this market penetration, simulation, and optimization model where we gather the data of the plans, the policies, all the techno-economics of the plan, because we're building on that. Policies around the world. So if we have a global case study, we need to identify all the plans. And then we simulate the existing policies to see how much revenue you can get or how much disincentive you can get, and compare it to the price of running the plants using the new technology. And then we can see if policies are sufficient or not. Now, if they are not sufficient, then we need to go to the optimization phase to see, okay, how do you design these policies over time? And when do you get to an economic tipping point? And what about uncertainties? So we can handle uncertainties simply by using sensitivity analysis or using more complex optimization methods. Now, for some studies, the method is very simple. So one leads to the other. But I don't know, every time we look at CCUS, it's more complicated than that. But the gist is the same. We collect the data, we analyze the data, but we also need to estimate, the cost of storage, cost of transport. We need to work out the market share, the WACC per country, the IRR. We need to understand cement production, for instance. So it's the same gist, but it gets more interconnected when it comes to some specific technologies, because to design, for considering cement plants in the UK, for instance, is really access to storage infrastructure that determines the balance of storage and you can comment and utilization. So I'll start from the first case study, which is integrated steel plants globally. Like I said, iron and steel is around us. We took the train this morning. you would have had a carbon footprint from iron and steel production. Or if you play music or drive a car, it's really, or your laptop is around us. And globally, there are around 385 integrated steel plants, so iron and steel in the same facility. And what we did was to collect the data for all these plants, working with like World Steel Association and several industries to make sure that we get the production capacity right, and the carbon emissions that we estimate per plant right or reasonable. Now, there are some plants, about 224 plants, currently use the blast oxygen furnace. Only 161 plants globally use the electric arc furnace. So there's some transition happening, and it is cost competitive to have electric arc furnace compared to replacing the natural gas in the electric arc furnace with hydrogen or having CCUS and blast oxygen furnace. So we have this distribution of plants and we have the data for all the plants. Another thing we do is to estimate the cost for all the plants of switching to, there are basically 6 technological pathways for iron and steel. So you could go from a blast oxygen furnace to integrate CCUS, and it will cost all these plants about $85 billion. Or you could go from a blast oxygen furnace to direct reduction with hydrogen. It could be blue hydrogen or green hydrogen. And as we expect, green hydrogen is more expensive. Now, you could go from a blast oxygen furnace to a direct electric arc furnace, and it's really cheaper than even a CCUS or blue or green hydrogen. The challenge with electric arc furnace is the electricity demand. So for the plants in Sweden, if they were to switch from a blast oxygen furnace to an electric arc furnace, they would need 80% of Sweden's electricity demand today. So there's an infrastructure challenge there. But you could also go for plants that already have an electric arc furnace where they use natural gas as a redundant. They could switch to hydrogen, and it will cost that amount for all the plants. So that's like the economic burden of decarbonizing iron and steel. Now, what we also did was to collect data on all policy interventions, so market-based policy interventions around the world. So you have some incentives for steel, you have some grant allocation for this sector. You have the emission trading schemes, so in Canada, the EU, something in China, Russia, and then you have countries that have a carbon tax, and you can see the carbon tax ranges from $0.8 per ton to 125.6, same as the grants range from nothing to still very little compared to what we need, the economic burden associated with decarbonizing the iron and steel sector. So what we then did was to see how much revenue can you get from these policies. So remember here, that's the cost to decarbonize the iron and steel. Okay. Oh, okay. I'm going to use a pen. So that's the cost for decarbonizing the iron and steel sector for different technological pathways. And if you look at existing policies today, this is how much revenue we get from them. So if I take case one, where we need $85.3 billion, under case one, the total policy support today around the world is only $33.2 billion. So that is for CCUS. It's not a bad idea, but what you see is industry is paying a lot because it's dominated by carbon taxes and carbon prices. So the incentive is only 2.2% contribution, and the grant share is only 3.8. And the incentives and the grant share is what government is paying. Now, for electric arc furnace, it's very small because the number of plants that we need to switch is also very small. But then you still see that we need 4.2 billion, but policies only contribute $0.4 billion. And when it comes to green hydrogen, if you're moving from a blast oxygen furnace to direct iron reduction with green hydrogen, the cost for all the plants is $434 billion, and policy support in terms of case three is only 46.8, and majority is driven by the taxes that industry has to pay. So in some sense, based on existing policies today, there's really no business case to decarbonize the iron and steel sector, and there's no mandate. So even if you have a mandate, there's really no business case. Everyone will struggle. Now, if we try to determine the optimal policy, so play around with these values of the taxes and the incentives so we can make that cost and see what the values really mean for society. So that means that we can get more out of incentives, get more out of taxes, and grants seem to not do so much because grants are not tied to any unique parameter, it's just a dollar amount. What we've seen is that policies that is dollar per ton of CO2 or dollar per ton of clean products are better. So we determine the optimal values, and I'll show what the values are in this slide. So now, if we pick 100% is the price of clean steel today. So to meet the cost, we need the green is an incentive of around $100 per ton for each plant on an average basis. It differs from country to country. And then we need a carbon tax that's just below $60 per ton and some form of grant per plant that is just around 0.6 billion on an average basis. So you need this combination of policy support to make it work. So this is like an ideal case if we are to make decarbonization of iron and steel using CCUS work, this would be the combination of policy support. But remember that today, existing policies only contribute $33.2 billion per year. So if you look at the total contribution from existing policies, that means that we kind of expect the cost of steel to reduce by 8% if CCUS is going to be cost competitive. So CCUS manufacturers can choose to do this analysis where they bring down their costs so they have a business case. So that's policy interventions working with technology developers. Because if they leave the cost at 100%, today's policies will not be able to get that revenue, will not be able to create a business case. So it's just 8% reduction in costs. I mean, it could come from manufacturers pricing low. It could come from energy efficiency improvements on the plant level to make today's policies work. Now, if we look at the second case, which is going from a basic oxygen furnace to an electric arc furnace, again, the price today is 100%. This shows the mix of policies. It's cheaper, so the incentive is lower, the price is lower, the grant is also lower, is in millions. And existing policies today give only about $0.4 billion per year, which puts us around this level. So that means that if we want existing policies to work, then we need to explore internal interventions within the plans to reduce the price of clean steel by %. So this will come from energy efficiency improvements. This could also come from how technology manufacturers price capture costs just to establish a business case. So everyone needs to play a part to make it work, not just policies, because still I don't think they'll ever be sufficient, but what do you do on the technology side to bring down the cost to make the policies work? Now, same thing for the third case, which is the most expensive. So going from a basic oxygen furnace to direct reduction with green hydrogen. I mean, we see for today, for a 100% case, if we want policy interventions to create that demand pool or to establish a business case, we need incentives as high as $500 per ton, which is very expensive. A tax as high as $300 per ton, just because green hydrogen is so expensive. But if you work with what's available today, which is 46.8 billion per year, which is somewhere around here, the cost will need to come down to like between 64 and between 30. So that's 46%. So you need to achieve a 46% reduction in cost for today's policies to be effective based on the financial flow. So that's a big stretch. 2% is possible. That's something percent is a big stretch. So today's policies do not support green hydrogen for direct ion reduction. Now, the fourth case looked at just blue hydrogen. Blue hydrogen is cheaper, so we need less policies today. And looking at the total amount at 33.2, we just need to bring down the cost to about 80, which is about 28% reduction in cost of clean steel through what you do internally with the plants, the technology is a big stretch. So for CCUS, it's possible, electric arc furnace, it's possible, but for the hydrogen options, it's going to be a challenge. Now, the third technological pathway was still green hydrogen, but moving from an electric arc furnace to DRI with green hydrogen. And again, we can explore what the values of the policies are using using the clean steel cost today, but also doing a sensitivity that as you reduce the clean steel cost, at what point do we not need policy support? That will be like the economic tipping point. So in this case, if you can reduce the clean steel cost by about 28%, then you wouldn't need any policy. But 28% reduction from technological savings and technological innovation is a big stretch. So you need both of them. Yeah.
So like 6% you just mentioned, like reduce the total policy cost so drastically?
Because it will be closer to the cost of dirty steel. So the gap you need policies for reduces. So that's why we have that reduction, and it gets to a point where you don't really need policy to drive the market. But this is where we are today. A 28% reduction is very unlikely in the next 5 years.
Yeah, but in the last one, it's only 6%.
Yeah. Yeah, in the last one, so one of them was just 6%. So it's going from black oxygen furnace to electric arc furnace. And the validation of this is there's a lot of trends. Most plants prefer to switch to electric arc furnaces than integrate hydrogen. Electric arc furnaces with natural gas, for instance, seems to be the medium-term technological solution because it's just 7% cost reduction needs to happen for it to get to some form of economic tipping point. And that increases with the choice of technology. So for green hydrogen, if you're moving from an electric arc furnace where you're using natural gas and redundant to green hydrogen, then you need this 28% cost reduction. And for the final case, when it comes to blue hydrogen, I mean, still expensive, but you just need about a 14% cost reduction to not need policy support or to align with what is available today. So in some sense, we'll say with existing policies, you don't have a business case, but we can explore what we can do on the technology end and on the plant end to further reduce cost, maybe through some energy efficiency measures or technology manufacturers just pricing a little bit low based on the availability of revenue. So from the first case study, I guess we can say that decarbonizing the iron and steel sector requires substantial financial investment, but today's market-based policies are insufficient to drive this widespread adoption of cleaner technologies. And it's best to combine. So these are optimal results that shows it's best to combine several policies instead of using only carrots or using only sticks, because you need to support clean steel costs, but you also need to tax the business as usual steel production. So the second case study is coming a little bit home to Europe. So we're looking at ethylene. Ethylene is everywhere in textiles. It's not just plastics and bottles, it's textiles and wood treatments. And I'm trying to potty train my 2-year-old because diapers have become so expensive, and diapers as well, and tires and cosmetics and electronics and pharmaceuticals. So it is everywhere. It is everywhere. And we looked at plants in the EU because of the EU's emission trading scheme and countries also having carbon taxes as well. So we looked at, that's the ethylene capacity. The highest is Germany, followed by Netherlands and France. And that's like the pipeline across Europe. And we took all the plants and tried to understand what the capacity is, the feedstock. Some of them we know, some of them we do not know. And then what the market share and the carbon intensity of each plant is. So we could see how MSMTO as the methanol synthesis, how that could work and how we could cost it. Now, this is just the annual carbon emissions from ethylene production. So Germany has the highest because it has the highest number of plants. And in addition to the EU's emission trading scheme, some countries have a carbon tax. So Poland has, Spain has, Germany also has, and that's the value of the carbon tax in euros. So this is euros, not dollars, euros for the different countries. So we looked at how the ETS and these carbon taxes can work to make decarbonization of ethylene cost competitive, or if it is cost competitive today. Now, this is just a simple, and diagram of what we found, right? So the first bar is conventional steam cracking. Now, if you add the carbon tax in all countries and the ETS, so this pool for decarbonization, you see that the price of conventional ethylene is still not high enough to make MSMTO a feasible option. So that's the price of MSMTO, so ethylene made from MSMTO process. And even if you tax conventional ethylene, you still cannot bridge that gap. Now, if you create a scenario where you could sell credits, because with the MSMTO process, it has negative emissions, a negative emission process. Even selling credits under the current ETS structure cannot reduce its price to make it cost competitive with conventional ethylene. And this is the picture what's happening today for all these plants. So in some sense, there is no business case for clean ethylene production based on today's policies. Now, what if we optimize to see if there can be a business case, right? So the average existing carbon taxes in our country stays the same because that's already existing, and the carbon price under the ETS stays the same. So we said, okay, what if you could have an additional carbon tax and an incentive on clean ethylene to close that price gap? So the incentive needs to be as high as 850 euro per ton, and the additional carbon tax needs to be as high as 500 euros per ton to make clean ethylene economically viable today. And look at what ethylene is used for. And this will give you a negative carbon footprint as well. But we only have 2.93 billion euros per year from the ETS as disincentive. So this is how much they will need to pay if they don't decarbonize. So that brings us around here. So that means that the price of clean ethylene will need to drop to around by 60%. So we're 100% today for today's policies to work. That's I don't like to use the word impossible, but that will be close to impossible to bring clean ethylene price. So that means that we need to increase the carbon tax or create an incentive for clean ethylene just to close that price gap. And we even did the optimization in a win-win way where, so the EU allows for hypothetication. That means that the tax you receive from a particular sector can be spent on that sector. So we said, okay, so let's say we want the government cost and the industry cost to be the same. So the taxes government really gets, they can use it to create this incentive over time. So it's like a secular policy framework as well. So it has a minimum cost to governments because they allow for it. And even at that, you still need a lot of money to support clean ethylene production today. So we've seen that current carbon pricing mechanisms, including the EU ETS and national taxes, are insufficient to make MSMTO commercially viable. We need to, of course, combine policies, but one of the biggest contributors to cost in this process is green hydrogen and CO2 because they are feedstocks for methanol. So if you bring down their cost, then you may have an economically viable solution, but you still need to increase the policy offering for this sector. The final sector we looked at was cement. They are also everywhere: chimneys, foundation, manholes, swimming pools. Like, you can't run away from cement, really. Um, and we looked at cement in 4 countries, and this is really based on the market trend. So 2 of those countries, the demand for cement is reducing. So the US and the UK. But for South Africa and India, demand for cement has increased by 96% in the last 5 years. So we thought we'll have a look at these countries. So in South Africa, we looked at all the cement plants. And we collected the data for all cement plants, capacity, location, so we can estimate because we're looking at carbon capture and storage for cement, we can estimate the cost of capture, the cost of transport, the cost of storage. And there is really no policy intervention for cement. So we are looking at what an emission trading scheme will look like, what a carbon tax will look like, what a capital grant will look like. In these countries, if decarbonization of cement using CCUS was to become an economic reality. We also look at the United States. So the United States has about 200 and something plants. So we collected the data for these plants. The challenge is always transport of CO2 because of how dispersed the plants are. But on the plant level, we can do the techno-economics and then work out how policies can improve the economic viability. And we did the same for India. So we collected the data for all cement plants in India to work out what the cost is, how much CO2 can be captured per plant, and things like that. And the United Kingdom as well. So there are like 10 operational cement plants. So we have an idea of the capacity and the cost of these plants. Now, what we then ask ourselves is, if you were to drive the economic viability of cement using single policies, what would it look like for these countries? So for instance, if there was a credit for storage, if a credit for storage was the only market-based policy intervention, what would the value be for these countries, taking into account the specific economics of each plant? And you see in India, the average is like 83. It increases to 417, depending on the size of the plant. There are bigger plants in India compared to South Africa. UK is particularly low because of access to storage and transport, and USA is the $215 per ton of CO2 for some of the biggest plants. And then when we look at what if you have a single policy intervention, so credit for use. Now, data shows that you can only use 5% of CO2 today. So the percentage for use is just 5%. That's why the policy intervention for use is very high. So you're only using 5% of CO2. So if a single policy like the credit for using CO2 is designed, that's what the values will be. And if you have a single policy based on a carbon contracts for difference, where you benchmark against a carbon price, that's what the values will be. And if the economic viability was driven solely on a carbon tax in these 4 countries, that's what the average and the maximum value will be. Interestingly, the average values are very close, but less than 30% of the plants are that value. More of the plants are the maximum value. So the UK is not doing bad, actually. Because with $83 per ton, that will put cement plants out of business, actually. With $83 per ton, you could create a good economic case. And then we explored combining the policy intervention. So what if we put all these policy interventions in the optimization model and determine what's the most economic policy intervention? And it came up with a combination, not the single one. So it's saying that In the USA, you need a carbon price, a carbon tax, a credit for storage, and some form of strike price for CCFD. So the US currently has a credit for storage, which is around that value. But for that to work, you also need some form of carbon price. Now, for South Africa, the country has nothing, but this is a combination of policy support and values from a bottom-up perspective. But I still need to think about the macroeconomic implications of all this value. But from the bottom-up perspective, those are the values of the policies you need to move the needle when it comes to decarbonization of cement. India and the UK as well. So you need some form of carbon price between 68 and 103. You need a carbon price under the UK ETS and a carbon tax, and then a credit for storage and a carbon contract for different to just top up of the UK's ETS to decarbonize cement. So what we've seen from cement is you need a mix of incentives, and the incentive is more cost effective. And these incentives are very sensitive to the price of cement and also the production capacity of the plants. And what we've seen is best to have bespoke policies, more difficult to coordinate bespoke policies per plans, but it may be best to have bespoke policies. And a one size fits all doesn't really work, except if you want to put the policies at the maximum value when it comes to a tax or the maximum value when it comes to an incentive. Now, at the beginning, I asked the question on can policy interventions improve the economic viability? And we've looked at iron and steel globally, we've looked at ethylene in the EU, and we've looked at cement in South Africa, UK, India, and the United States. I guess I can say that based on today's policy interventions, they are not enough to create sufficient demand pool for heavy sectors if we rely solely on policies. And a lot of these sensitivities we did show that we need other forms of internal interventions from what you can do to reduce costs on the site or to improve the performance of these technologies which will drive down the cost. But also across these sectors, you can see how the values of the optimal policies change. So it will be difficult to have a one size fits all. Maybe some more tailored sector specific policies are necessary, especially for heavy sectors that are very heterogeneous. But what we've seen continuously from even what we've done for shipping and aviation and green hydrogen is you need blended interventions from public finance, from private finance, and from technological advances, almost like we need these three to happen at the same time if we are to get to the economic tipping point quicker. Now, there is a white paper on a new way of thinking about incentivizing industrial decarbonization, also integrating end users into the picture. So you can scan this QR code to have access to the white paper. It was developed by Imperial, coordinated by the Leonardo Center. So it's a cross-faculty white paper. So please scan the barcode to have a copy of it if you're interested in this space. And I think I can come to an end. So I want to first of all thank the three people who worked on this database. So Harry worked on iron and steel, all the 6 pathways. Gila worked on ethylene, and Ed worked on cement. So I'm really grateful to them. I'm just a messenger here, and I also supervised their work as well. So thank you for listening, and I'm happy to take any questions.
Talking earlier on about the cost of some of the, I suppose, more advanced low carbon technologies like green hydrogen, and the cost for those is obviously really big. Is that cost because they're the whole kind of supply chain for that is not technology ready yet? Is that cost factored in, or is it assuming that the technology readiness for some of the parts of that supply chain are already there? Is it's not ready, or is it because it's just expensive?
Both.
Both.
Both. So in the cost, when you're estimating the cost, there is the innovation bit, which is the technology bit, and there's a demand pool bit, which is the supply chain bit. So the combination of both, but majority of the cost will come from, there's really no demand pool, so it's very high, because on the technology side, you cannot build bigger electrolyzers, for instance, if the infrastructure is not there or the electricity demand is not there. So it's a combination of both.
So is this assuming the cost of the products comes down first, and then the producer will switch to a cleaner solution? Or is happening, like, what is sort of the order in which that needs to happen?
So we link the cost of the product to the cost of the technology. So if you're integrating CCUS into an iron and steel plant, the cost of the product will depend on the additional cost of CCUS, right? Now, on the cost of the product side, what will create a demand pool or a good business case is if the cost of the product from the CCUS integration is the same as the business as usual, right? For some, or you could look at just the technology cost of CCUS. Most industrial players are happy to pay like $30 per ton to get rid of CO2, because that's how much they pay for waste. So you could say, how do you bring down the cost of capture from like $200 per ton to $30 per ton? So what we do, we keep an eye on the two. We keep an eye on the technology cost coming down and its impact on the cost of the product, because one comes down before the other in the analysis. So we track that relationship between them. So that's why the cost reduction for the different technological pathways are different. But they are related. So the cost of the product is dependent on the technology choice as well, and other things, but majority of the cost breakdowns from the technology cost.
Could you flip it the same way as well and say, as the technology cost comes down and
Yeah.
the product cost remains the same, you have the same tipping point inversely?
So if the technology cost comes down and the product cost does not come down, I'll be worried. That means that you've been able to intervene in the technology, but the cost of the product is still very high. So you may get an economic tipping point. So we call it like an internal tipping point for the technology, but the product that sends the market signal is still very expensive. So we compared MSMTO with all these options, and MSMTOs compared to this group had the best economic evaluation in terms of the techno-economics. So that's why we took MSMTO forward to do this analysis. Also, MSMTO has been demonstrated at scale. So we can then do this analysis to get a demand pool. But the other two, we've not seen any demonstration at scale. We've seen them in research papers that they can work. So that's why we picked MSMTO forward. But MSMTO is not the only option to decarbonize ethylene. So let me go to iron and steel, because that's where we show the breakdown of quality. Okay, so today, in today's market, the ETS has the biggest pool So 26.4% of the economic case is from ETS, 6.5 from carbon taxes globally, and just about 2.2 from incentive. But to get to a future where everything can work, the ETS is still 33, carbon taxes go up to 37, and incentives need to be around 28%. I'll take you.
Thanks for a very interesting presentation. I was wondering, I hope it's not too off topic, but I was wondering if the same sort of analysis could be applied to, rather than a technology, more like a strategy for operation for a plant, for instance, or something like that. So I work on the water industry where the main carbon footprint comes from the energy use, for the electricity use. And I was wondering if a more advanced energy management strategy that includes, say, demand response, for instance, but also puts the utility at risk of not meeting their targets for water supply, say, if you could apply the same sort of analysis, like financial, so incentives.
If that will work on an organizational level, that will work. So depending on their strategy and their plans, we could do the economic analysis, and once you estimate the cost, so capex, opex, staff, everything required to deliver their strategy and the distribution of the cost, depending on what they will do. Then the question is, is there a business case to make that investment? So you can look at policies. Water is funny because water is not part of the ETS, but there could be like some innovation grants available, but private finance is also available to see how you can create a business case. Basically, because if you do the analysis on a firm level, the NPV will be negative. So really what's required to get it to zero in terms of revenue.
Was wondering if you've done a benchmarking exercise against the mainstream scenarios like the NGFS and IEA, their current policy or equivalent scenarios, your findings?
We picked the technological pathways from the IEAs or IRENA or anybody that has used an IAM to say, okay, these are the pathways that could work for the sectors. And then we take it on the plant level to break it apart. So it's not benchmarking against their policies, but benchmarking against the pathways that they've come up with. Then when we evaluate the existing policies or we design new policies, we then validate with what they are saying. Now, most times it aligns because the analysis is not on a plant level. It's most times on the project level, on the sector level. Most times it aligns or is within the range. So if we come up with an analysis on, so if we take the pathways for iron and steel from the IEA and ARENA, we see all the common technologies on these pathways and see what the wedges are for these technologies and integrate it on the plant level to find the optimal mix, we could come up with, oh, we need a carbon tax between X and Y. Now, if you go back to the IEA studies and all these, whether it's within the UK or different countries, they could suggest a carbon price that is P, that is between X and Y. And P could come from some macroeconomic studies that they've done. So we say, okay, if P is between X and Y, then we're probably speaking the same language. Or at P, this is the only market share you can have. So somehow we need to integrate both concepts to come up with a carbon price that we can have a higher market share from the top down and from the bottom up. I try not to reinvent the wheel. I don't think there's time to reinvent the wheel, but really just understanding what's happening on the bottom up and how we can really create this demand pool. Because the plans are going to make the investments at the end of it.
Thank you.
There's some more online questions. Someone else. If the hydrogen is part of the cost for transition technologies, so what prices did you assume, and have you explored the price of hydrogen that would help reach the tipping point?
So the price of hydrogen depends on the location of the plant. So I used these prices, there's a large range. So I worked with the minimum, the average, and the maximum. But we had another presentation where I showed how blended interventions can get to an economic tipping point for hydrogen. I think it's available on YouTube. So that one was just focused on hydrogen because hydrogen is really key to a lot of these transition pathways. And I've shown how policies, using the UK as a case study, policies, financial interventions, and the technological advances and bring the price of hydrogen down. And I did this analysis from now to 2050.
So ask what would happen cost of DRI if grid infrastructure is.
So when we took into account the infrastructure required, the cost will go up. The cost will go up because the electricity demand is more than, for most of the countries, is more than 20% of the existing demand just to electrify iron and steel. So the cost will double, more than double actually, if we account for green infrastructure. And to make case two more expensive.
How do options compare on a specific plant basis, so DRI EAF versus blast furnace?
So this is very similar. So on a plant basis, the cheapest was electric arc furnace, of course, without considering infrastructure. But even if you double that cost, it's still about $10 billion per ton. Green hydrogen was the most expensive to deliver the same amount of CO2 reduction. Green hydrogen was the most expensive. Electric arc furnace was the cheapest, followed by CCUS, blue hydrogen, and then green hydrogen.
Any other questions? Because there are a few more online, but I don't want to. Someone said green products may fetch premium price in the market, and that may reduce carbon tax and the incentives required.
Yes, that's very correct. So if there's a premium price for green products that is acceptable by the market, then we can factor that in to reduce the policy intervention. That's why I said we need somewhat of a blended interventions, really, if we are to achieve an economic tipping point quicker.
Final question, I think, relates back to the MSMTO question. It says, does MSMTO account for the revenue product?
Yes, it does. And it also accounts for, because MSMTO is a negative carbon process. Yes, it does.
Any other questions?
Thank you all for coming. Have a lovely rest of the day.